is an introduction to linear algebra. Linear algebra is a field that you can apply to a ton of different fields of science, such as mathematics, natural sciences, social sciences, computer science. And it turns out that linear algebra at its very core is mostly based on solving systems of equations. And so right here I have 2x2 systems of equations. And this is a problem that you encounter a lot in algebra to find the solution to this system of equations. So let's think about what type of methods we could use to solve this system. When you're exposed to algebra, you typically come across three main methods to solve linear equations, which are, first one's graphing. You can graph the solutions. Graphing. There's also substitution. Substitution. And finally, elimination. Elimination. And it turns out that this third method, elimination, is the one that is most important to us in linear algebra because it's the most organized and the most methodical and the most systematic. Graphing, for example, is not the most practical because it's not very precise. We can't construct graphs that are exact enough to get us an exact solution most of the time. Especially when we have fractions and decimals and we go into higher degree systems like 3x3s, 4x4s, graphing just becomes impractical and also very not mathematically rigorous. Substitution would actually lend itself well to 2x2 systems such as this one. You could, for example, solve for x1 in this first equation. You get x1 equals 2x2 minus 3. And then you continue and substitute that in the second equation, get an answer very simply. But as you go into higher degree equations, higher degree systems, substitution becomes less useful and more complicated. But elimination, on the other hand, generalizes very well to higher degree systems. So we use elimination extensively in linear algebra. So let's go ahead and do elimination for this system right here, see if we can get an answer. So elimination. Alright, so what we can do here, recall in elimination, we multiply the equations by constants so that the coefficients match up, and that then we can subtract them from each other and then eliminate some of the variables. So here what we're going to do is multiply the first equation by 3, and then we'll have the 3x1 in both equations that will cancel out when we subtract. I'm going to write the second equation first. 3x1 plus x2 equals 5. And then 3 times the first equation. 3x1 minus 2 times 3 is 6. 6x2 equals negative 9. And we're going to subtract these equations from each other so that we can cancel these two 3x1s. That's going to leave us with 7x2 equals 5 plus 9 equals 14. Alright, and then we've eliminated the x1, so now we're just left with a one variable equation. And this is relatively straightforward to solve. We just divide by 7. X equals 2, we already have one of our variables. To get the other one, we just substitute back into our original equation. We can take either one, x1 minus 2, x2, which is 2, equals negative 3. And solving for that, we get x1 equals 1. If we want to write that in interval notation, we could say x1, x2 equals 1, 2. And there we used elimination to solve that system of equations. So again, this is pretty straightforward if you've been exposed to algebra. But it turns out that in linear algebra, it becomes necessary to develop a more methodical, a more uniform way to write all this elimination. Rather than have all these x1s, x2, these variables, we use what's called matrices. A matrix is defined as a rectangular array of numbers. We could have, for example, 5, 7, 14, 20. I'm just coming up with random numbers. And we surround them with brackets. And they could have any number of rows and columns. We could have 1, 2, 3. That could be our matrix. That could be a 1 by 3 matrix, and this is a 2 by 2 matrix. But what's particularly important for us is using these matrices to represent these systems of equations. For example, to represent this system, we could write the coefficients 1, the coefficient of x is 1, coefficient of x2 is -2, and the constant term is -3. So that's our first equation. And then the second equation of the system, we can write x1, 5. So there you can see we're just, this matrix is telling us the exact same information as the system of equations, but we omit the variables x1 and x2 and the equals. They're all implied. It's just that using this matrix notation, it's much more easy to easily access information about the system. For example, if you look down the columns, all the information corresponds to each other. This first column is the coefficients of the first variable, x1, 1, 3, and over in the algebraic notation you see 1, 3, -2, 1, -2, 1, -3, 5, and the original -3, 5. So, not surprisingly, we can extend elimination to apply to matrices by doing what's called row operations. We do operations on the rows of the matrices so that we can basically reproduce the methods that we're doing for elimination using the algebraic format. So what we did originally for elimination was we multiplied the first equation by 3, right? So let's go ahead and do that for the matrix. We're going to multiply the first row by 3. And the way we write that out is we say that we're going to multiply row 1 by 3 and stick that into row 1. Our new row 1 is going to be 3 times the previous row 1. So row 1 times 3 is going to be 3, -6, -9. Row 2 is going to remain the same for now. Next, what we did was we subtracted the two equations from each other. And how we're going to, the equivalent way to say that in terms of matrices is we're going to add the opposite of one row to another row. So here's how we're going to write that out. We can say we add -r1 to row 2 and stick the result in row 2. That's going to give us a new row 2. Row 1 is going to stay the same, 3, -6, -9. But row 2 is going to have the opposite of row 1 added to it. So 3 plus -3, that's 0. 1 plus +6, that's 7. And 5 plus 9 is going to be 14. And then finally, we can reduce this last row even further by dividing out the common 7. The first row is going to stay the same. And for the second row, we're going to have 1/7 of row 2 is going to go to row 2. All right, so 0, 7 divided by 7 is 1, and 14 divided by 7 is 2. And now we can translate back from matrix to algebraic form to see what this is really telling us. This is telling us on the bottom row that we have 0x1 plus 1 times x2 equals 2. And on this top row we have 3 times x1 minus 6 times x2 equals -9. We can eliminate this redundant 0x1, and we can just say 1x1, 1x2 as x2. So x2 equals 2, and substituting back into our first equation, we can find x1. 3x1 minus 6x2 is 12. Add 12 to both sides, we're going to get 3x1 equals 3, or x equals 1. And not surprisingly, this will give us the exact same solution as we got during the elimination, the more algebraic format, which you just have to realize here that we're following the exact same steps. The row operations that we do on our matrices are exactly the same as when we multiply our equations by a constant or when we subtract our equations from each other. So hopefully this gives you a little taste of the different approach we take toward linear systems in linear algebra, and we'll expand on this more in further videos.